Good afternoon, everyone. Thanks for being with us. Well, I say good afternoon because I'm in Montreal. I don't know where you are. So hello, everyone. Thank you for being with us. I'm Héloïse Edom. I'm a research associate at the Institut l'Énergie Trottier. And thanks for being with us today for our discussion regarding the infrastructure and how to operationalize the transition to carbon neutrality. It is one of the most recent report in our Canadian Energy Outlook series of report. A few words about the Institut l'Énergie Trottier. We were created in 2013 thanks to a philanthropic funding from the Trottier Family Foundation, and this support was renewed in 2023. Our mission is to mobilize science and governance to help catalyze the transition to a decarbonized Canadian energy system. Our areas of action focus on supporting training and research, contributing to analysis to help to design responses to energy issues, and to contribute to communication of the issues, the needs for action, and highlight some of the solutions. Some of our main projects are one is about developing an evaluation grid for a biomass project in the context of Carbon Neutral Canada that was led by Roberta, which is an research associate at the Institut. I work on a project related to reducing peak electricity demand in an electrified environment and improving resilience in an increasingly electrified world. Another example of our project is the energy modeling hub that is directed in collaboration with the University of Victoria and University of Calgary, and this pan-Canadian organization aims at developing and supporting the energy modeling ecosystem in Canada. The presentators today will be the main co-authors of the report. So it will be Normand Mousseau, who is professor of physics at the Institut at Université de Montréal, and he is the scientific director of the Trottier Energy Institute. And the other main co-author is Simon Langlois-Bertrand, a research associate at the Institut l'Énergie Trottier. Today, the presentation will be the main authors will explore the nature of the transformation needed to reach Canadian net zero and Canadian carbon neutral environment with the angle of the infrastructure needed. They will comment on the transformation that will affect the evolution of technology on energy production and energy services. And they will also comment on some avenues to operationalize this transformation. So I will let the ground to my colleague, Simon. Sorry, a few words before Simon start and unmute itself.
Yeah.
The question will be at the end of the webinar. The report is already published on our website, and the slides of this presentation and the recording will be published a bit later, but the report is already available. Thanks. You can go, Simon.
Great, thanks, Eloise. Hi, so just to situate this report, to expand a little bit on what Eloise said. So this is part of the Canadian Energy Outlook project. So we're in our third edition now. These are reports that cover, well, we first do the state of current energy systems across the country and GHG sources. And in the latest edition, which started last year, we published these reports in different parts, right? So first the state of things, and then modeling of net zero pathways to 2050. And the analysis and the discussion of these results help us identify some strategic issues that we delve into in further reports. So one of those was published a few weeks ago on the decarbonization of off-road transport, and this is the second one. on infrastructure deployment and operationalization of the transition. So this is in parallel with a series of work we do on some of these issues. So one on biomass analysis, assessment, and decision-making support tool, one on the management of peak demand, and a few others that have been ongoing. So I encourage you to look at our website to see the schedule for publication for some of these. So if you can switch the slide. So just to start or use as a starting point, the very high level results of the modeling done in the earlier part of the Canadian Energy Outlook. So similar to what others have found, when you look at transitions to net zero at the aggregate level for economy-wide emissions, you notice that achieving carbon neutrality requires very substantial GHG reductions, but importantly, these demand very major technological transformations in all sectors, from energy production to services. In addition to this and these reductions, there's also a requirement for a substantial contribution from carbon capture and negative emissions activities in particular, which are currently largely question marks and struggling to take off, right? So the idea when looking at this is that these transformations will have a profound impact on daily life, which is not clear in the models, right? So the delivery and the use of clean energy, for instance, dominated by electricity to a large extent, as we'll get into, paves the way for new ways of doing things that are very difficult to predict and imagine today. Just like 120 years ago, no one understood really the implications and the ramifications of switching to an oil-based economy. Similarly, today, it's very hard to predict the extent of the transformations in the delivery of services. But there's a few large trends that we can look at now and that help us understand what is necessary on top of the parts and the components of net zero pathways, what is needed from a structural perspective, and we'll focus on infrastructure for today. So on the chart here, you have the evolution of the energy mix for energy consumption. And you can notice that achieving carbon neutrality requires the massive electrification of services. And this helps reduce total energy demand in the case of our results by 9% before 2050. So this is despite very large population growth, despite the increase in GDP figures as well. So there's a significant reduction in total energy consumption, and it's driven by two opposing trends. So the first one is perhaps almost by definition in net zero pathways, a dramatic reduction in the role of fossil fuels. And the second trend, which partially offsets the first, consists of a doubling of electricity production by 2050. So the evolution of the energy mix across the country is therefore accompanied by a profound transformation of all Canadian energy sector, or economic sectors, I should say, which affects both energy production and consumption. But this requires an evolution of the structures that underpin the delivery of energy services. So this will be the main topic of this report and the presentation. I'll now let Normand pick up from here.
Thank you, Simon. So indeed, what the model predicts is clearly a deep transformation of the energy system if we want to get to net zero. However, the model itself does not explain how we will operationalize this transformation, how we put it in practice. It also does not address the collateral consequences of this transformation. So some of them are relatively clear. We'll need electricity infrastructure, but the question is how much power and when and how should we deploy it has to be discussed, and is to be understood that electricity infrastructure will be determining how fast we can decarbonize. So it has to be built ahead of the need. We cannot think of it as all coming in a total synchrony. Also, these model underline the need for new technologies to decarbonize processes and some applications, and we'll come back to this. So what's missing in the model is also interesting to look at. And finally, from the model, and we'll come back to that also a bit later, there's clear indication we'll need capture and sequestration of CO2 to very high level. And this is unavoidable. And we need to understand how we can deploy this at the scale and at the speed at which it's required if we want to get to net zero. This transition, therefore, to make it work, we need structural changes, but we need to do them in a strategic way in order to get there in time, understanding that we'll need to create new supply chains. Old supply chains will disappear. We need to adapt service chains that in manufacturing use installation repair. So we have to change the way we're doing some of that. And therefore, we have to focus, to understand this report will focus on energy production. But before that, let's look at the consumption technologies in various sectors. So we'll look at three sectors: building, transport, capture and sequestration of CO2. So three sectors that are using energy. We're leaving aside industry because industry, and in fact, industry in agriculture, because industry is very diverse and cannot be covered in such a general report. So we'll need to have some deep dive more specific to this sector. And agriculture also is extremely complex, so it needs its own analysis. So we leave them out, but for the other, it's relatively easy to see the interlink between all these approaches. And of course, the fact that we're decarbonizing some sector means we'll need more electricity. So we need to understand how the energy production and the transformation of the energy production system is linked to these transformations. We will finish by discussing the cost of the transition and whether the timetable can be met or not. So let's start with the sectors. Let's start with the building sector. Our modeling, and essentially all the other models, decarbonize the building sector, both residential, commercial and institutional, almost totally when in any scenarios that get to net zero. Why? Because the technology needed for that are known. There are electric-based technologies, as you see here, for example. You see this line here. That's the energy demand for the building sector in a decarbonized society. And you see it's mostly electricity in light blue, with fairly few other energy sources. This electricity will not serve as heat to produce heat directly, but rather to move heat through heat pumps, either aerial heat pumps or geothermal heat pumps. So we have this technology, and in that sense, it's the kind of the simplest sector to decarbonize, formally, at least on paper. But the challenges are important. This is if we want to get to the midway path by 2035, because building decarbonize very quickly, in principle, they should be to get to zero before the other sectors, so before 2050. So do this, we would need to keep the speed constant over the next years to decarbonize more than half the fossil fuel-based heating system in Canada by 2035. So that means essentially we would need to decarbonize. You see, you have about 8 million households that still heat with fossil fuels that would need to be electrified. So half of those by 2035, that's 4 million houses to do in 10 years. So that's a lot of transformation. Same thing when you look at the institutional, commercial, and industrial building. We would need to have at the same level, you say we have about 600,000 of these buildings that still use fossil fuel, and 87%, so 90% of those should be decarbonized by 2035. So there's two issues here: decarbonization of each building, but also ensuring that we have the electricity needed to support this electrification. So when we think of that, we need to really develop, I would say, a systemic strategy for this electrification. So as we are electrifying a small fraction of these buildings, we don't really need to worry about the whole system. One can add here and there a heat pump. But if we want to replace 50 or 90% of these buildings, then clearly we need to think in a larger setup. So to get to these numbers that we see, it's essential to replace all gas and oil furnaces with heat pump. It's important to do that rapidly, which means that we have to stop, as of today, any new building to use fossil fuels heating systems. Otherwise, we're piling up since heating systems have a lifespan that is about 20 to 30 years. So what is blocking this today? We have initial high costs, especially when we're talking about high-rise building, multi-unit residential, commercial. There's no standard solution that is offered for these types of building. We need to assemble them building by building, so that's costly, that's risky, and we don't have a clear setup to support the formation of skilled labor, to support the creation of a service industry. Moreover, there is clearly a perceived risk associated with these new technologies. It's not only perceived risk. We've seen in a number of industries that decided to move to heat pumps, that these heat pumps did not perform well because they were not installed properly, they were not used properly, they were not adjusted. So there is a need to create this infrastructure. So if we want to operationalize this transition, it's not sufficient to only subsidize heat pump for the client. There's something that has to be done much broader. And it's even more important for Canada because Canada has largely been treading water on these issues. So we're kind of waiting to see what's happening without real strategy to ensure the deployment at the right level. So Canada needs to have strategies to support the installation of equipment, training the workforce, standardization, develop strategies to decarbonize some sector where we can put more effort, and when we can train, we can test, we can standardize to facilitate the installation, to reduce costs and prices. We need to work through all this aspect to reducing the barriers. And we have to find where Canada can benefit from the added value of this transformation. And I think when you compare in the rest of the world, we are almost at the same level when it comes to electrifying large building, multi-residential, commercial. So Canada, more than the residential, where this is well established over the world, Canada could do something by developing a strong service industry that could be exported. So we think that there's a place there to both work on accelerating the transformation in Canada. We haven't been doing it at all at the right speed, but also benefiting economically from this transformation. And if we do it well, we can lower prices and therefore we can make this much more competitive. We have to understand that electrifying heating will have a massive impact on the electricity network. I'll discuss that from the side of the utility, but let's just understand what that means from the demand side. Today, in most provinces in Canada, the peak demand for electricity is in the summer. So it's a few months in the summer. And this peak is slightly above the average over the year, but not so much. As we electrify, we'll see a massive transformation in the peak, in the demand overall, with a very strong increase in the demand in the winter. This is here a 2-year average power demand for Quebec. Quebec is the most electrified society in Canada and one of the most in the world, and most of the residential heating is electrified. And what we see here is that in the summer, the maximum demand that we see is about 20 gigawatt. For about 3 months in the winter, we see a winter plateau of demand, which is about 33 gigawatts. So 60% more than the demand in the summer. Over that, we can have a few tens of hours in the winter which are very cold and where the demand can increase to 40, 42 gigawatts, so much more than double what we have in the summer. That means that we have to be able to support this type of transition to winter demand, and this will not be done by simply buying this energy to our neighbors, because as everybody electrify heating in the north of North America, we won't have access to markets that have huge surpluses in the winter. So we'll find all these regions having surpluses of electricity in the summer and extremely strong needs in the winter. And we need to think about that directly. So those are challenges for electricity distributor because we have to finance infrastructure that will serve like 3 months out of the year. How do we fund this? How do we support that? So for this, we need to meet basic winter demand. We need to manage fine peaks, and we have a report coming in the next few weeks about this analysis, more specifically, how we can do this efficiently. There will be a need for balancing demand management versus investment. As I said, there will be strong limitation in how we can exchange for peak. So the demand will be matching all over Canada in large part, not totally. So we need to understand how to do that efficiently. And that's not a reason for not electrifying, not decarbonizing, but that's a reason to do it strategically and efficiently and start thinking of it immediately before we start transforming. And that can be done efficiently. If we don't do this, we'll find the distributor refusing to electrify some services and delaying decarbonization and leading to investments, sunk investment in technologies with fossil fuels that will have to be removed over the next few years. And we already see this even in Quebec, where regularly Hydro-Quebec says no to new clients who would like to electrify some services. And that really is not helping in the decarbonization. Now, let's look in another sector, the transport sector, that is much more complex than buildings because there's a diversity of solutions. There are many unknowns about the type of solutions we have. And there's also much variety in the maturity of the various solutions that are on the table. So I'll be discussing the road transport, personal vehicles, goods, as well as rail, sea, and air transport. Off-road transport, which is everything else, will not be discussed because it's very broad, very diverse, complex. And so we published a few weeks ago a report that is specifically targeted to this sector, in part because we feel that Canada, by having an aggressive and very strategic approach to decarbonizing this sector, could really establish itself as a world leader with strong industry in that field. So I invite you to look at this report that was written led by Simon Langlois-Bertrand. So let's look at the personal vehicles. In our model, what you see here is the type of energy consumed per million passengers kilometers. We see that by 2050, most or essentially all of these vehicles will be zero emission and will be electric, all electric. That means clearly that to get there, we can count on the fact that we have a ZEV mandate, so zero emission vehicles mandate. That means that by 2035, all new vehicles will have to be electric, and that's how we get to this. But from an operationalization point of view, this needs to be supported by sufficiently available public charging infrastructure, which is not today available at the right level. If we now look at the energy consumed by type of energy, we see a huge drop in energy demand between now and 2050. So why? Because electric vehicles are about 3 times to 4 times more energy efficient than combustion engine vehicles, because electricity is work. So we have much less loss in heat. So when we think about efficiency, electrifying most services, I'm focusing here on transport, but it's the same thing in building. The best way to get energy efficiency in the system is by electrifying. So there is, even though we know we can get there, even though we have the technology, it's known, even though this technology is cost competitive as of today, nevertheless, there's still work that is needed by government to support the change and facilitate and reassure the Canadians as they move away. Now, let's look at freight. Freight is also, I'm still drawing here, the type of energy consumed per million tons kilometer. What we see is by 2050, we can also decarbonize this sector, but it's no longer a single technology that dominates. Here in our modeling, we find 3 competing technologies: hydrogen at 47%, batteries at 29%, and catenaries, so cables that would run over highways where trucks could kind of pull their energy from as they run. Essentially, those dominate those are essentially three technologies that could be used. So that works in a model because you can distribute these technologies. In real life, of course, it doesn't make much sense to build infrastructures for each of these technologies in parallel because those are costly, those are competing for the same capital, and it also makes the whole challenge of running a system with multiple competing technology for the same service very complicated. So clearly, the model underlies the need for better analysis and strategic development to limit the choices and understand which is the best solution out of those. Okay. When you look, again, I want to emphasize this, if you look at the energy consumed per type of energy, we see again that by electrifying this transport, we will decrease by about a factor 3 the energy demand in the road transport and for freight. So what are the strategic choices? These choices will depend on the environment. For example, if you look at EU regulation for drivers of lorries, what we find is that lorries first cannot exceed 100 kilometers per hour. They are blocked at that level. More or less, truck drivers have to stop every 4 hours for 45 minutes break. And in this context, you can see that the EU will have a strong strategic interest to move to battery-operated lorries or heavy trucks because it's possible to have a battery that holds for 4 hours, and it's possible to recharge them in 10, 15, 20 minutes, even today. So over the 45 minutes break, it's totally possible to handle these recharging. In North America, however, we will not have, and we don't have the same regulation for drivers. We have longer distances, faster speeds. So clearly, we have to consider the other technologies and evaluate which one are best. And because trucks travel over long distances across countries, we will need to standardize these choices. We have finally to understand that beyond regulation, the choices will be made on a number of reasons. The cost of deployment, but also the impact on other systems. For example, battery charging in catenaries will require increased generation and a finer alignment between production and demand. If you think of hydrogen even done by electrolysis or blue hydrogen done, for example, by from methane with carbon capture and sequestration, then there will be less impact on electricity or will offer better flexibility in how it can be produced. However, moreover, it will provide storage flexibility so that it's possible to use stored hydrogen instead of pulling all the time on the electric network. So all this means that to go forward, we need detailed analysis, but we also need pilot projects, for example, to test these technologies. There's a strong risk for Canada of not, if it doesn't move rapidly, to see its technological choices imposed by the US. And if you let the choices imposed by the US, then it means that Canada will not be able to develop its own ecosystem. So we think there's a strong opportunity for Canada to move rapidly on this, even with a few states in the US, and try to see how it can develop a strategy that is beneficial for Canada. Finally, as we rethink freight transport, it's important to rethink the balance between road, sea, and rail transport because all this will have an impact on energy demand and the type of infrastructure we need to build. Talking about this, let's go to rail transport. In our third edition of the Canadian Energy Outlook, we see that rail can be decarbonized. In our case, we decarbonize it using hydrogen and electricity, 60%, 40%. So that's on paper again. What will be the real technological choices remains to be seen. There's a number of unknowns in this sector, and also a different structure. When you think about freight transport, you see a very broad number, a very large number of operators, where the government have a much stronger role to kind of align the technologies. Here, this sector, the rail sector, is dominated by a few players only in the North American scene. These players have a lot of revenues, a lot of profits, and they invest very little in their infrastructures. So the role of government versus these dominant players is different than from the I would say the freight, on the road freight. Here, the government have kind of to push and orient these dominant players, put regulation, put clear dates on what it wants to see, some milestone being reached, in order to really get these players to move on this issue. Because it also need to align this demand of the vectors retained for this transport with, for example, the trucking industry, because then you could have also scale benefits and other advantages by trying to kind of integrate these solutions. So as we move on this, clearly there will be regional and continental solutions that will be beneficial. So Canada will not be able to do that alone, but needs to be, I would say, proactive in this field. The role of Canada, of the government here, will be to support the transformation and to help develop this continental vision. But given the fact that there's few players, this can be more about pushing and pulling than really doing all the decisions. If you look at maritime and air transport, we also do model this in the outlook, but we don't really see any economically viable solutions. So the cheapest solution that comes out in our models is to keep using fossil fuels and use negative emission technologies. That means we remove the CO2 from the air, either through biomass or directly, and extract it and bury it somewhere. The solutions available today that are zero are much more costly. So decarbonizing this sector is not something that Canada can do alone. Those are numerous challenges and it requires international coordination. However, Canada has significant competitive advantages here and therefore should be present and invest and be among the leaders in developing these low carbon emissions. Part of it because it has significant resources in bioenergy and low carbon electricity capacities. It is also a world-leading aerospace industry. And to be able to support these industries and try to leverage its resources, Canada should also be developing strategies quickly on researching the proper solutions for those, or getting prices lower on the solutions we see already. So what can we say as a whole regarding transport? So transport energy infrastructure is larger and more diverse than building infrastructure. So because building is essentially putting heat pumps in buildings and then upgrading the electric grid from distribution to production. But it's an upgrade. It doesn't change fundamentally the nature of these infrastructure. When we think about transport energy infrastructure, as we decarbonize, we need to rethink a lot of these infrastructure. We need to build new that will be different. Even when we think about charging infrastructures, even for cars, we're moving to 1 megawatt power that is being needed for the most recent Chinese EVs, for example, that can recharge in 5 or 6 minutes. You really need to get to a 1 megawatt power charging station. If you move to trucking, this will need to be even bigger. So we need to see how we build this infrastructure. If we go to hydrogen, we go to catenaries, those are different infrastructure that need to be shared among many players, but that need to be structured also across borders. These choice of technologies will influence infrastructure to be deployed, the type of transformation on the vehicles, but also the impact on the other energy infrastructure. So we need to be able to think about this, and therefore there's a need for public leadership in funding regulation to reduce risk and speed up the transition. I'll give one example. The circuit electric, for example, in Quebec for charging station was started in 2012, so 13 years ago, and has contributed a lot to reassuring Quebecers as they move to buying electric cars, because they know there will be charging stations available everywhere that are working good quality, either close to the home or when they travel. And this, in addition to subsidies, was essential to give confidence to people that they can move to this. In the rest of Canada, the charging station circuit is much less developed and is not as conducive to making the jump to electric cars. There's strong productivity gains when we move to electric cars and as we electrify transportation. We will find ourselves with more reliable, less expensive vehicles. We'll have also better control, performance, productivity of these services. So we have also to understand these gains as we move forward and see how we can use these gains to redeploy capacity workers in other fields where more workers will be needed to support the transition. Now, let me talk briefly about the crucial role of CO2 capture and sequestration. In our model, as you saw that Simon showed you earlier, we can get to net zero by 2050. But this is net zero, it's not an absolute zero. So we still have emissions in agriculture, in industry, but we have also negative emissions. That means that, for example, we're burning biomass, taking the CO2 and burying it, or we doing direct extraction from air. Those are expensive technologies, but in addition to these technologies, we also have a lot of capture of CO2 at the industry, at the smokestack. And so when we put all this together, we find that we will need to get net zero in 2050 to capture and sequester about 160 million tons of CO2 every year. That's about 25% of today's total emissions in Canada. This is huge. We don't think that this will happen because some of these emissions also indicate that there are issues with decarbonizing certain sector, and we need to develop the net zero technologies. But we'll need a lot. And when you compare this number, 160 million tons is equivalent to what we have been producing in terms of oil from the oil sand in 2023, which was 170 million tons, and is also much less dense, so it takes much more space. Now, CO2 is a gas, so in terms of space, it's huge also. So how will we do that? We have first to reduce the amount that is needed to be captured and sequestered by introducing zero emission technologies, but also we need to work on how we can reduce prices and make this happen. What are the challenges? We think that there are kind of three main challenges to get CCS at the level we need, in part because, and we need to do that fast. When we look at how much we need to grow, even to get to the level I was talking before, the level of CCS today is about 1.5 million ton captured every year in Canada, mostly from oil mostly used for oil extraction. To get to what our models project, we will need to multiply this industry by 125 years. If you compare what that means, because this is a heavy industry, compare that to oil sand that has grew only by about a factor 8 over the same period between 1995 and 2023. Okay, so that would mean 12 times faster than oil and gas industry. So clearly we need to do other things. But even with this, I was saying there are three challenges that need to be met. We need to increase the capture rate of CCS. We need to reduce energy costs. And we also need to validate the geological resources that are promised or that should be used to sequester the CO2. So let's look at the capture rate. The theoretical potential that was promised by the industry and that you see in the literature is about 95% for concentrated emissions, which means when you have a few percent of CO2 in the air. The industrial reality, however, has turned out to be much lower. Boundary Dam, Quest, and WR Sturgeon are all below 80%, between 65 and 75%. Glacier is the only one, which is a power plant in Alberta, to be close to that at 89%, but there's still a gap between 89 and 95%. So clearly, we need to improve that. We need to invest and understand how we can increase that to at least 95%, because every CO2 molecule that is not captured there will have to be captured by other processes that will be more costly, through, for example, that direct air capture. There's also large energy cost. If you look at the glacier example, you require about 2 gigajoule of energy per ton of CO2 capture at the stack, okay? Which for a direct net cost of about $30 a ton, if according to Entropy, who is leading this project. If we take these numbers that are very optimistic for a 5% CO2 concentration, capturing 100 million tons would require 56 terawatt hour a year and $3.2 billion, okay? And if you include the fact that you will have lower concentration in many cases, that this is optimistic cost, the reality is probably, both in terms of energy and cost, around 3 to 4 times bigger. So this is very important. To make this CCS competitive and useful, we will need to reduce the energy demand still further, or reduce the cost of energy. It's important to understand that we cannot run these processes only with intermittent energies, because these processes don't handle well variability in the process. So lowering the temperature, increasing temperature, changing the fluxes. So all these processes, to be very cheap, need to be constant and run at high scale. We also need, finally, to validate the resources for CCS. Canada has a potential of 100 billion tons of storage, but we need to assess the real constraint, the risk, and also we need to model other ways of storing, for example, through biochar. So I will not go more in detail for this, but I invite you to look at the report. So for us, there's a huge opportunity for Canada, because we can build on the forestry, we can build on the oil industry to be able to develop a new industrial sector, CCS, which would have a worldwide importance. So production of chemical compounds, geological storage, construction of facilities, we can rely on clean energy, mainly electricity, and Canada, because of its industry, could have multiple sources to support this and test this and validate these technologies. There's a lot of obstacles, but they could be lifted with sufficient will. Okay, so let me move quickly to energy production. As Simon said earlier, we'll need massive electrification. Our model project doubling the energy production from 650 to 1,300 terawatt hours, with mostly constant hydropower, with multiplying by 4 the nuclear industry, by 8 the wind, and scaling up a bit the solar, but still in background, because solar is not so well aligned with the demand, which is mostly in the winter, as we have seen. Part of the issues is that our models tend to underestimate the increase in demand in electricity due to some biases in the technical and economic model. So we use a very conservative approach to the development of new sector. We don't include AI, we don't include greenhouses that will be very high, large consumer of new electricity. So this will raise the demand. Also, we consider that energy use is optimal throughout the chain, which is not the case. People don't always install the most optimal solution. They don't always use it well. So clearly we'll need more energy. If we only think of Quebec, for example, Quebec has received industrial projects for more than 13 gigawatts of power, which is a third of what Quebec can produce today. So clearly it's impossible to answer this demand today. But it's an indication that demand for electricity in new sectors is growing. So Canada will need a lot of clean energy, and we need to start building now. but we need to understand the value. We can look at simply the price of new kilowatt hour. When we look at this price, we see that wind and solar power offer the cheapest electricity, well below any new other technologies. However, wind and power are intermittent. That means that the demand is not always aligned with the production. And that reduces the value of this electricity. So to really get the real value for intermittent, we need to add storage. Okay. And happily, massive storage solutions are in development. Prices go down. We see how between 2013 and today, for example, the price of batteries has gone down by a factor 8 or so. They're still going down today. Other batteries for mass storage are being developed, metal air battery, which are much cheaper than lithium. So we have solutions that are coming, but it's clearly important to understand that as we move to having more and more intermittent production in our energy system, we can no longer think only of the kilowatt hour. We need to think about the alignment between production and demand. And that's why solutions like nuclear energy, even though it's very expensive compared with intermittent, has the advantage of offering a base load that is constant and that has a significant value. However, nuclear is not appropriate for the type of to cover, for example, for the difference between summer and winter demand. So we will need a broad range of solutions. We'll need to develop large-scale storage that is long-term storage that is not as necessary in warm climate. So that's also an advantage here for Canada to develop technologies that are appropriate for Canada, other countries, but that are not today at the forefront of interest of the rest of the world. So as we move on, we need to make major investments. We need to construct ahead of the demand like we did 40 years ago, not wait for the demand to occur because otherwise we'll slow down the transformation. We need to realize that as we electrify more and more, the role of electricity for civil security will be always higher, and we therefore need to also build security, safety, redundancy in the system that is not built today in the electric system. Electricity from renewable is cheaper already today from electricity from fossil fuels, but we still need to solve the issue of balancing through interregional transmission line and storage. Let me finish briefly by saying that the cost, when we look at the cost of this transition, it will provide a net benefit from the system. We did a calculation a few years ago that was published in the second edition of our Canadian Energy Outlook, where we showed that even though investment until 2050 for the electricity grid will be very high, we're talking about $1.1 billion, the saving will be enormous. So in oil and gas, starting from 2050, we'll be saving in expenses something like $75 billion a year. So overall, there are major economies from moving forward. So we should move forward, but of course, the saving will not be distributed fairly. So there has to be some political will to think about how we can do that. And I want to emphasize that these numbers are not fake. When you look at the numbers from Hydro-Québec for its investment of $185 billion to produce another 50 gigawatt of power, 50 terawatt hours, sorry, of energy and 9 gigawatts of power by 2035, plus upgrading the grid, we see that counting only the terawatt hour, we would save considerable money by 2035. Simply by the fact that we can electrify all cars, still have 20 terawatt hours on top available for free, and pay essentially all the $185 billion by the money saved on gasoline. So we see already that today it is less costly to make the transformation. And that's kind of for electricity. Simon will discuss how we can see this on a more global scale.
Thanks. I'll be quick because I see the time flying by. But just to restate the point about cost, When we compare the projections we made in 2021 and what came out of modeling in the latest edition last year, you can see that the marginal price of reducing GHG emissions up to 80% of today's level has gone down by almost half, right? So it shows you that a high carbon price is not the only possible driver of decarbonization, which in turn means that it's possible to deploy sectoral strategies that target the most appropriate tool depending on the conditions, right? Whether it be regulation, cost of pollution, or support for technological development, for instance. Next slide, yeah. Yeah, so about the feasibility and the timeline, I mean, Norman touched on a few of these, but we have some eras in the past where we saw a similar rate of transformation and deployment. So there's definitely some inspiration there. But the point is that the discussion should be about the barriers that are slowing down the evolution of these transformations, and in particular, which are preventing costs from going down more quickly. So in the report, we provide a lengthier discussion for the specific cases of buildings, parts of transport, and electricity production, to a certain extent, CCS as well. But these numbers, including the labor requirements, these are large numbers. But when you put them in perspective and in terms of the savings that they help produce for the entire economy, they do represent sufficiently small fractions so as not to undermine the rest of the economy, provided, of course, that the necessary support is there to redeploy human resources in line with the needs and everyone's aspirations, of course. So this is a considerable effort, but with a strategic approach, we think it's possible to accomplish progress pretty early on. So the strategy overall that we think is missing is to have at least an overall vision with societal objectives involving all actors, just to really show and translate what are the benefits that we stand to gain from these transformations. Instead of doing this on a case-by-case basis, the parts of the pathway really think about the structural transformations that allow this to happen and allow people to realize the benefits. So this means like an approach that targets priorities and innovation in particular. There's a lengthier discussion in the report on what you can conclude from this and what kind of approach should be developed, but I'll be a bit quicker here. So when you look at scenarios for achieving carbon neutrality, it's clear that they seem to impose extremely rapid structural changes on the economy as a whole. But the point here is that when you assess the challenges facing various energy consumption and production sectors, it shows that a sustained pace is possible, both structurally and financially for sectors, at least especially where decarbonization technologies are already well identified. So we talk about buildings, parts of transport, electricity generation in particular. There are others as well. And so to remain competitive, there's an interest for Canada to deploy strategies that will enable its citizens and businesses to access existing technologies at prices similar to those observed abroad, but also benefit from identifying carbon neutral technologies that we can develop valuable intellectual property on. Right? So whatever we decide, there's been remarkable progress and the world is moving pretty quickly. And so it highlights really that there's an opportunity to take advantage of this context in the short term. Thanks a lot.
Thank you, Simon and Norman, for sharing with us your analysis regarding the infrastructures and their transformation to reach a carbon neutral Canadian society. I invite the participant to share the question in our Q&A tool, but maybe we have 5 minutes left, so maybe I will start with one question. You mentioned that there's still a lot of development and innovation that is needed in air transport and also maritime transport to be, I would say, developed. What would be some tools that could help Canada to improve its performance in this sector for decarbonization, or at least to improve collaboration with at the regional level?
In fact, what we've seen, therefore, first is that Canada has a lot of biomass. So one of the One, it cannot solve everything in terms of biomass, but it could help at least decarbonize some of these sectors. So how can we use this biomass, and how can we leverage this to enrich the forest sector, for example, while allowing the development of solutions based on this for fuels, for example, net zero fuel. So it won't be perfect, but that's one way to move, for example. Canada can also see how can we use the electricity sector that we have, or the hydrogen, the fossil fuels we have, to make hydrogen that could be used, or ammonia, even though there's a lot of energy losses. That's why they don't come out of our model, because what we see is this is very costly solutions. But Canada has at least some resources that are thought to be one way to move forward, even though it's costly. So Canada could invest in these technologies and try to have startups, try to have an industry that can see how it moves. We can also move on the other side, on the aerospatial side, and see what they can contribute. So it's kind of both ways in some way, only on one sector. It's the same for maritime. We're building some ships, not that much. We have less than we use, but we have a small industry. We also, in terms of train, it will be North American. So the role of Canada is bigger there to develop some technologies.
Thanks. I would say on the same, more or less the same subject, do you know any collaboration at the North American level regarding decarbonization of these sectors, or is it still something that's not happening yet?
The rail industry has projects, and they're cooperating and pushing some project on hydrogen, for example, together. It's always complicated because you have some rules about competitiveness. So the government have to act in some way to facilitate these exchanges between competing companies. So they always walk and say we can collaborate, but not so much. So I think there's an effort to be done between them and also the people who build these engines, for example, to try to facilitate the pilot projects and the sharing of the information.
Yeah, I would add for maritime decarbonization, that's a really tough one because the action is going on pretty much only at the European level at this point, or at least, very largely. And of course, it depends on the routes, right? So the port infrastructure has a very large influence on the actual possibilities. So if at one end you have certain technologies being deployed, either you catch up or you propose something else, but you have to decide very early on, right? So it's very difficult for Canada to impose its preferences. But one more reason to actually get involved to make sure that nothing puts us at a disadvantage in that area.
Thank you, Norma and Simon, for all your thoughts and all your time with us today. I see the time is flying, so I will again say that our report is published on the website, and the slides and recording of the webinar, of today's webinar, will be available soon. So this afternoon was the English version, but you will also have the French version that will be available. So again, thanks everybody for being with us today.
Thank you. Bye.
Thank you.